So let's talk about a shortcut. Let's talk about the fact that sometimes instead of just calculating all of those voltages, I do have obviously three, for example, at this point resistor. They're going to ask you a question. They're going to say that, oh, tell me how much voltage drop you had on the second resistor. So based on last one we learned, we have to find the total current, then we have to find the voltage drop for the second one, and then we have to some kind of prove it or not. But let me give you a better way. What would happen if I can find that specific voltage by using a law or a rule that we call it as a voltage divider rule, or VDR? What does it say? This guy would say that instead of just finding the current first, the I total first, then find the voltage drop is going to be Ri, I'm going to give you a formula that only in series. Guys, still we're talking about the series second. The Vx, that x could be any number, that could be 1, 2, 3. Vx, or the voltage drop for a specific component, is going to be the amount of resistor that you have for that specific component divided by R total, or the total amount of resistance that you have, multiplied by ET. ET is our voltage source, is 12 volts. So at this point, my V2 would be what? Would be 20 divided by 60 multiplied by 12 is going to be 4 volts. This 4 volts is going to be the same thing that we just found. This rule is called as a voltage divider rule, is a very important rule that you have to memorize. That proving that one is not that kind of a big deal, but it doesn't make any sense to do it right now. But try to memorize it. Try to think about it intuitively. The more resistance you have, the much more amount of voltage drop you face. When we are going to use this one, if we want to do the quick single point voltage checks, in circuit designed to create a specific reference voltage, for example, at a point if they ask you, do we need to have the 10 volts of voltage drop for that specific resistor, or you have a load that only can handle 10 volts, and based on knowing all of those resistors, you can find the reference voltage. And when current is a primary concern, as you just saw, the I total wasn't primary concern, because the only thing question asked me was how much is the voltage drop. It didn't ask me the current. Yes, indirectly asked me about that, but why should I find it when I do have a better way? So another thing that we do have inside our very important part of the circuit is power. If you guys remember, we were talking about energy, and energy is in joule. It is important, it is everywhere. Energy could be in electrical format, it could be in heat format, it could be in mechanical, it could be in any format. But what would happen if you're talking about the power inside a circuit, or the power related to each component? The very first thing that you have to know is the definition of power. Power means the P is W, which is going to be energy, divided by time. The amount of energy that you're going to consume over time is something that we call as power. What is the unit for that? The unit is watts, that we use it with just W. By the way, this W and this W are completely different. This is watts, and most of the time we just use the W itself. So this is the very intuitive definition of power. Right now, I do have a scenario. Again, I do have my question itself. So at this point, I would like to find the power. How much is the energy is going to be consumed by that specific component over the time itself? That's a real question. So before just finding the power or amount of energy that's going to be dissipated in each of these components, let's talk about three important formulas that we do have related to that. The very first one is V times I. It means that voltage times current still is going to give you watts. Another one is R times I squared, or I squared times R is going to give you the power itself. So how come we do have this formula? Again, you can just look at V. V actually was Ri. So what would happen instead of just the normal voltage, I'm going to have Ri, then I'm going to implement it inside this formula. I do have what? I times R itself. I'm going to implement it inside the first formula. Ri times I is going to be Ri squared. Simple as that. The last one, which still we can derive it from the first one, is going to be V to the power 2 divided by R. Why we use that? Because sometimes you do have the current, you don't have the voltage. It would be better to use the second formula. Sometimes we do have another one, vice versa. You can use the third formula. Or when you do have both voltage and current, you can use the first formula. At this point, imagine that I do have my, by the way, this 200 is not right. We're still talking about the series, right? This guy should be here, for instance. This is 200 ohms. Cool. So let's talk about that. The P1, or is going to be power inside the 1, since we do have the resistor itself and the current, it would be better to use the RIS squared. What do I have? I do have the R, 10 ohms, times the current. The current is constant all the time for all of those components, right? So I do 0.2 to the power 2, and based on the R or resistance, I do have 0.4 watts, I do have 0.8 watts, and I do have 1 watts of the amount of power is going to be dissipated inside of each of those components. Another thing that we know, just like the KVL, the total amount of power or energy that is going to be produced by the source itself, because a source is the source of energy actually, right? But at this point, since we do have the W divided by T, the amount of energy is going to be produced divided by time, we do have watts. So P total is going to be P1, the amount of dissipated power in the first component, plus P2 plus P3 is going to be 2.4 watts. The 2.4 watts also can be derived from another method. PT, or amount of total power, is ET, which is the total voltage, is 12 volt, times IT, which is 2.4 watt. We see that we still have the same number. Very important thing. Each component has a maximum power rating. It means that each of your component that you have can only handle specific amount of power. And if something happens and some kind of power is going to exceed this amount, this guy is going to be destroyed. And for example, in our some kind of the examples that you had, R2 was 0.8 watt and R3 was 1.2 watt. These guys would require resistor rated for at least 1 watts and 2 watts. It means that if you don't have the resistor that has minimum amount of rated power inside of itself, your resistor is going to be burned. It's going to be something like this based on the amount of power that is going to be injected to that part. So some kind of the roadmap that we have is step-by-step analysis procedure. The very first one is that we have to confirm the path. Right now, we are going to talk about the series circuit. It means that is it going to be truly series one, or only one, or we are going to only have one path for current? Remember, some of you would ask, what does that mean? Imagine that I do have the voltage source like this. I do have my R1, I do have my R2, but my R3 and R4 are a little bit different. At this point, I do have something that I call as parallel. We still don't know about that. I will talk about it. But it means that the whole thing is not series. Only these two are in series. So when you find the total current, whatever, you cannot say that IT is equals I1, I2, I3, and I4, because these two things are to be completely different. Remember. Finding the total resistance, R1 plus R2 plus R3, it means that all of the one are going to be series, add them up. Find the total current, we know I total is going to V divided by R total. So it's going to be voltage divided by R, so you have your current in amp or milliamp. Then find the individual voltage. Either you can find it based on V1 is R1 times I total, or based on the voltage divider formula. Vx is Rx divided by RT times the input voltage itself. You can do that. Then you can verify your work or using the Kirchhoff's voltage law. You can say that V1 plus V2 plus V3 is going to be the V source itself. And finally, if they need it, you can use 3 formulas that I just taught you in order to calculate the power itself. So let's talk about a little bit of voltage drop that we just mentioned, and we are going to talk a little bit about node voltage. What is that? As I just told you, in electronics, voltage or voltage drop is completely meaningless if you don't have any source point. What does that mean? It means that voltage, the V that we have, actually comes from the difference of potential, or delta V comes from the fact that your voltage is the difference from higher point to the lower point. All the time, you do have 2 points you have to consider. When we are talking about the voltage source as is 12 volt, actually means the difference of voltage from the top to the bottom is 12 volt. So when we are talking about the voltage or voltage drop of specific component is, for example, 4 volts, means the difference between the higher part, which we know it as positive, and negative part, which we know it as negative, is going to be 4 volt. So again, the voltage, or the right word is voltage difference, is completely meaningless when you're only going to talk about one specific point. So we're going to talk about that. So we call the reference, we call the guy that most of the time we're going to consider as a ground. Why we use ground? Because we know, and this is a fact, ground has a 0 voltage. The difference of voltage between ground and itself is 0, and most of the time we use it as the reference itself. So when we're talking about 12 volt at this point, for instance, we are talking about the difference of this point and this point. The negative part is going to be considered as something, we call it as ground, which we show it something like this, or we show it by G. The V subtracted by VG is going to be 12. So first, let's talk about the voltage drop. As we know, voltage drop means that how much voltage that specific component is going to steal from my voltage source. And in order to measure that, we do have a component, we do have a device as a voltmeter that has 2 sides, positive and negative. Since right now I'm measuring the voltage drop for a specific component, I have to choose 2 points. Positive, mostly on the top, the one that is closer to positive section of my source, and negative, which is closer to the ground. So this is voltage drop, and we know that's 4 volt. As you can see, I do have the difference between VB and VC as my voltage drop in R2 itself. So this guy is going to be double, so it's going to be double subscripts. It's going to VBC. It means that VB subtracted by BC means the voltage difference between point B and point C. Why that matters? But because the very first thing is about the safety. We have to know where the ground is. Common reference for multiple circuits. Again, we use the G as reference, and in order to simplify all of those complex analysis, we need to know that. Another concept that we do have is node voltage. Unlike the previous part that we had 2 voltage, some kind of points, and on both sides or both leg of our resistor, voltage node means that the voltage of a specific point respect to ground. For instance, when we say that what is VA and we don't have the second subscript, means that what the voltage of a specific node subtracted by the voltage of ground. What is the difference of V and VG? VG is all the time 0, right? That's why we call it as VAG, or we call it as just VA itself. Specific points will be called as nodes. When you have the voltage difference between one point as ground, we call it as node voltage. When you have the 2 difference of points that while none of them is ground, we consider it as voltage drop. So at this point, A is going to be my node, and B is going to be my node, C is going to be my node, and each time I would like to find the voltage difference between that specific point and ground. So when you have single subscript, means that the voltage at point B with respect to the ground. For instance, example, the point A, the top of R1, VA is going to be 12. It means that how much is the voltage difference between this point and ground itself. As you can see, either you can consider all of these voltages, add them up together, or you can simply say that this VA subtracted by ground is going to be VA subtracted by V ground, which is directly connected to your source as 12. What about VB? VB means that how much is the voltage difference between this point and ground. Either you can find the voltage of this guy, add them up together, or you can find the voltage of this specific point, which was VA. V subtracted by the amount of voltage drop that was considered because of these 10 ohms, or we can say that subtracted by VAB is going to be your VB. And that is completely makes sense, right? Because definition we had VAB was VA subtracted by BB, right? Instead of just having this formula, I do have this formula. Simple, right? So I do have the VA, it's going to be 12. I found the VAB by finding the current, and then by some kind of using the voltage formula, or maybe using the voltage divider. V1 is R1 divided by R total times the total V. I can find the voltage drop, which is 2 volt, 10, 12 subtracted by 1 is going to be 10. What about point C? Point C is going to VA subtracted by this voltage drop and this voltage drop. Is going to be 10, that we already found it from the VB itself, subtracted by 20 times the current, which is going to be 4 volt, and I do have 6 volt. And if, again, we do have that, VBC is going to VB subtracted by VC, which is going to be 4 volt, is going to prove our wording. So that was the difference between the voltage drop and node voltage itself. Be careful about that. So from the theory to reality, this is something that I love, because from now on, everything is going to be serious. Not serious, it's going to be serious. Why? Because we are going to measure them. What is the definition of voltage or resistor if you don't have any equipment to measure them? Yes, by having the calculation or some kind of using the calculator, find some voltage, I can find some current and maybe resistor, that is fine. But then I have to use it in the real world scenario. That's why we do have special devices for them that we call it as multimeter. The multimeters are there in order to measure the voltage, current, and resistor in real world application. For measuring the voltage, we are going to use this specific section of our multimeter. We call it as a voltmeter. By the way, probably for the next chapter, I'm going to talk about my voltmeter that I have. It's going to be some kind of very common in almost everywhere. You do have different kind of multimeters, by the way. But this specific one that I have, it's going to be very basic. It's not that basic, but as you can see, it has different sections. It has the digital part. It has the knob itself. It has this kind of hose on the bottom that you can use in order to measure them. So I will show you how you can use this special device, but you have to give me a little bit of time because I'm kind of waiting for special things that are going to reach me hopefully in these days. But probably I will talk about the voltmeter, how you can use that. Maybe I will test it with just the battery itself to see the voltage. But unfortunately, we don't have the equipment right now to measure the currents or some kind of resistors. Probably in a couple of days I will have them, so don't worry and stay tuned. But just before that, we have to learn a couple of things, right? How to handle that. And the most important part is breadboard. Breadboard is your playground. You have to have a place in order to connect all of those resistance, the voltage source, and everything together. For the next chapter, I'm probably going to talk about my guy, which is going to be the breadboard itself. But just before that, probably we are going to touch other parts because we don't only have the serious construction of our circuit. We do have other parts. We will talk about it. Don't worry, one step at a time. Cool? So, I have a voltmeter. Voltmeter should be connected in parallel. It means that if you do have a circuit like this, I do have 10 ohms, I do have 20 ohms, and I do have 30 ohms. I will talk about it, why we do have this way of connection. Just imagine that right now, I do have everything like this one, and then I do have it's going to be negative 12 volt is over here. If I would like to measure the voltage, the only thing that I have to do, I have to connect the positive side. As you just saw, we had some kind of 2 holes or 3 holes to be specific. So we are going to use it as positive side and negative side of my voltmeter. Then I have to make sure that I'm going to adjust the setting to be at DC. Then I can measure the voltage drop as we just calculated. If this considers one as positive side, this negative side, I can find the voltage drop, and you will see that I do have the 4 volt as my number itself. What about measuring the current? As you just saw, voltmeter is going to be connected in parallel. Why connecting in parallel? Because the amount of resistance inside your voltmeter is so high that somehow we can say that guy is not going to allow any current to pass, because as we just learned, I is equals V times R. If we assume that V is this constant, for example 10 volt, if we increase the resistance so much, your current is going to increase. And if your R is something around positive infinite, your I is going to be around some kind of 0 and small and small and smaller. So the voltmeter has a very high internal resistors, so they are not going to have any effect on the system, so don't worry about it. Then we do have our ammeter. The ammeter still is going to be inside the multimeter, but with different settings that we do have over here. So we have to connect them in series. As I just told you, instead of just having a wire, we are going to connect the positive and negative section of our ammeter to the system. It means that at this point we had a wire, but right now, instead of just that wire, we are going to connect this one. It means that if we assume current goes this way, it goes this side, then goes inside the ammeter, goes outside of the positive, the negative, and goes back to the normal itself. So nothing has changed. Why? Because emitters have very slow internal resistance. So they're not going to add up anything to the whole system. Yes, they're going to be connected to series, but they're nothing. So very common mistake that we do have is that about the short circuit. So be very careful. I will tell you how we can have the short circuit problem, and also about the incorrect readings. Means that you do have the positive and negative section. Sometimes you're going to connect them backward and you're going to read negative rather than positive. By the way, when we are talking about the positive and negative, we are talking about the positive and negative in voltage drop and current. As I just told you, just moving from positive to negative side of my voltage source is going to be considered as a positive direction of the current. If you connect it backward, your number would be negative. Also about the voltage drop, the difference between the higher end and lower end is going to give you a positive. But if you connect it backward, by connecting backward, a voltmeter or your ammeter is going to be backward. Because the red guide or the red, some kind of wires, most of the time considered as positive, and negative one, or is going to connect it considered as black one. So if you connect it backward, instead of just reading a number, you're going to have a negative. It's not going to be problematic right now because we care about the absolute value of number, but in the future, you would face a couple of issues related to that. So please be careful. And another thing would be about the current settings. For instance, if you're trying to measure the DC, but then you apply AC settings, obviously you cannot see anything, or vice versa itself. So let's see some series circuits in action. By having a couple of examples in the future, we are going to talk about it. What does that mean? So right now, I do have my voltage source itself as a 12 volt. I do have a resistor. I do have something that call it as LED, light emitted diode. So this is a very important component in electrical circuit, and it has a specific formula attached to that. But right now, just assume it is just a lamp, right? The lamp is connected to circuit, and I'm going to turn it on, right? So the thing is, or the problem that we do have right now, is an LED requires a specific current, for instance 20 milliamp to operate safely, but our source provides too much voltage. This is the time that I told you we use resistance. We have the RS for a reason. Why? Because your LED cannot be connected directly to your source. If you use the Ohm's law, the resistance inside of LED is not that much. And V or I is equals V divided by R. Imagine that you have 12 volt and you are going to divide it by, for example, 0.5 ohms. You're going to add a huge amount of current. LED or any kind of components has a limit in handling the current itself. So if you inject too much current in your LED would be broken down. Maybe you smell that, or maybe you hear banging or noise, or anything your LED is going to get down. That's why I have to limit the amount of current. Unlike the fact that I would like to use the full potential, but right now I have to limit it. That's why I'm going to use the RS. But here's the question: how much this RS should be in order to make sure that I do have the right amount of current? Imagine that I do have a LED that only can handle 20 milliamp. It's not that much, but I do have a 12 volt. How I can have something that can only handle 20 milliamp? By using the RS itself. How I can find that RS? The solution is simple. The RS is going to be the voltage difference between the source and LED itself divided by ILED. How we got that? So here's the thing. We know R is equals V divided by I, right? And also we know for a fact the voltage over some kind of the voltage, or the voltage difference over RS, partially, or the positive part, is connected to 12 volt, right? So we can call the, for example, A and B would be VA subtracted by BB divided by I. So VA is 12, right? When we do have VA, what about VB? VB is not directly connected to this part that we knew it as our ground. Right now, its guy is connected to LED. This guy is also at the end considered as a resistance, because we know LED is a load. Load is going to consume some voltage, so we do have voltage drop there. So the voltage drop, or the amount of voltage this guy is going to consume, is not that much. Most of the time it's just 0.7 volts. It's completely negligible when we're talking about 12 volts. So the voltage of LED should be subtracted by the voltage of 12 volts, and then I do have the voltage drop over here. Divide that one by the current itself, I can find the RS. Is that so? That's why we do have this formula. For instance, if I assume that I do have a 9 volts and the LED is going to consume 2 volts, which is a little bit high right now, but most common LEDs, they only consume 0.7 volt, or the voltage drop is just 0.7. And an LED, we know for a fact, should only handle 20 milliamp. I have to have the 350 ohm for RS to make sure that my LED is not going to have any harm itself. What about creating the voltage divider? What does that mean? As I just told you, that the voltage divider is a simple formula. The Vx is going to be Rx divided by R total times the voltage itself. But assume that right now, instead of just using that formula in order to find the amount of current or finding a right resistance, I don't have access to a resistance of that Rs. So is there any way that I can decrease down or limit one voltage? And I would say yes, there is. What is that? By using the voltage divider. What does that mean? It means that actually I'm going to divide my voltage source into two different parts, in R1 and R2. By choosing the right number, I can make sure that amount of voltage or voltage drop that R1 has is going to be in a level that R2 or any kind of things that could be connected to another load is going to be completely safe. That's why we are going to also use two different resistors as what? As a voltage drop, or in order to make it as a voltage divider. What was the problem again? We have a 12 volt source, but the specific component needs 5 volt, right? The specific component needs 5 volt. It's your specific component is your, for instance, LED. And LED is going to be connected. By the way, this is something we call as parallel, and the parallel connection means that the voltage of LED right now is the same as the voltage of this guy. We will talk about it in the future. But imagine, or some kind of assume, that if R2 has 5 volts of source, means that there is hypothetical voltage source that is connected to your LED, and everything is going to be okay. So the solution is over here is this. We are going to use two resistors in series so they can divide the source voltage, creating the stable lower voltage output at their junction itself, and that's something we like. And what about the sensing circuit? So what is the concept? One resistor in a series pair can be sensor, like a thermistor or some kind of the photoresistor. These are specific kind of resistors that are going to be sensitive to heat and light, which is kind of resistor is going to change with condition. So as the sensor's resistance change the voltage at the midpoint, we are going to change also proportionally, by the way, allowing us to measure the temperature, light, and etc. So probably in part of this work, I will talk about different kind of resistors, that we don't have only one normal resistor that's going to consume all the time. Sometimes we do have resistors that are going to act as sensor by increasing the temperature of the room. That guy is going to increase or decrease. By having more or less amount of light, that guy is going to decrease and decrease, anything related to that. So here's a troubleshooting. When good circuits go bad, what does it mean, troubleshooting? Troubleshooting is a very important part of each electrician or each electrical circuit path. It means that everything seems fine, but you do have issue. Your voltage source is connected to your load, but your lamp is not working, and also everything is fine, but you will find out that the current, for example, should be 200 milliamp, but it's 0. So what is going on? This is the time that we have to do troubleshooting. We have to check that maybe one of the components is not right, the connection has a problem, or maybe the source is not connected. What is even happening? So we have to consider this kind of expectations in our work in order to handle that specific solution, or in order to troubleshooting. For instance, I do have 12, it's just calculation. Imagine that because of a problem, the wire is going to be broken. The wire that I used over here was broken. So what would happen on that time, or is going to be burnout or whatever? The symptoms of that is going to be like this. My I total is going to be 0. It's completely expected, because if your path is broken, no current can go through. So that's why your current is going to be 0. Another thing is that voltmeter is going to read the full 12 volt. Why? Because if you connect your voltmeter to this part and if you connect it to that part, I don't have any current over here, means that the amount of voltage drop that this guy has is actually how much? V is R times I. It doesn't matter how much resistance do I have, my V is going to be 0. It means that if I assume that this voltage, again, voltage and current are different things. It doesn't mean that at what point you have voltage, or you don't have any current, you don't have any voltage. Voltage is another thing. So it means that at this point, I had 12, and at the same time, at this point, I didn't have any voltage drop, or it was 12 subtracted by 0 is still 12, right? So if we connect my positive side to 12 volt and the 0 side is actually connected to ground, no current goes that way. So I don't have any voltage over here. So the negative side is going to be connected to 0. So my voltmeter is going to read what? 12 volt. That makes sense. That is something we call as open circuit. What is the short circuit? The short circuit means that a wire or solder bridge accidentally or bypassing the component. It means that right now, my 2 ohm, instead of just being by itself, is just a wire. Right now, the current goes this way, and instead of just moving through, R2 is going that way. One specific characteristic about current is that current all the time is looking for the least amount of resistor or the resistance. Why? We know electrons would like the easiest path. So having the least amount of resistance means that easiest path. So instead of just current goes this way, this guy goes this way. Is that so? So if you connect the voltmeter to your point, it means that you're measuring the voltage difference in a wire. We know that wire doesn't have that much of a resistance, so the voltage of here, if we consider as V, and if we consider as VBB, these two guys are going to be somehow the same. That's why your voltmeter is going to be 0, right? So by RT, right, RT at the beginning was R1 plus R2 plus R3. But right now, imagine that your R2 is gone or is just replaced by a wire. So R2 is gone and your R total is R1 plus R3 itself. And finally, changing in the component value. Imagine that resistor fails and its value is going to drift significantly. Instead of just having, for instance, 100 ohms, I'm going to have 90 ohms because of some problems. So what are the symptoms? The symptoms are circuits works. You have current, you have voltage, but the readings are incorrect. They will be lower. I mean, at this point will be lower. Why? Because your resistance is either going to higher or lower. If we imagine that at the beginning of the point, we had this resistor as, for instance, it was 50. How much was that, by the way? It was 30, right? So imagine that instead of 30, this guy is going to be converted to 90. So I total was V divided by R total, right? V was something constant, 12 volt all the time, but RT is increasing. If RT is increasing, IT is decreasing, and well, we see the voltage for each of those guys is going to decrease as well. All voltage drops will be different from the expected values. By this way, you can find out what is going on. So this is going to be the slides about the lab preview. And in the lab part, we are going to talk about everything that you can see in the picture. An important part would be about the voltage source, that we do have it as 12 volt. That 12 volt could come from a battery or could come from a voltage source itself. And another important thing is something we call as breadboard. As I just told you, breadboard is your playground. If you would like to connect all of your components that you will see over here onto something, you have to have a playground. So breadboard is your playground. On another hand, we do have our voltmeter we are going to use in order to measure the voltage, current, or anything related to that I will completely talk about that one. So, summary, what we did. At this point, we were talking about the series circuit. What was the circuit at the beginning? Then what is the series circuit? Combination of everything that was connected side by side, and they had two important rules. The very first rule was that if you disconnect any part of your circuit, it's going to be completely collapsed. And the second rule was that the current on all of them would be the same. Another thing we learned was about the voltage drop, anything related to about the Ohm's law, how we can find the amount of power dissipation, something related to the current and would be about ammeter, something related to voltage would be the voltmeter, how we can troubleshoot that, and so on and so forth. So right now, we talked a little bit about it. We talked a little bit about some kind of questions. Again, try to rewatch this, and if you have any question, comment me down below. Maybe some of you would say that, could you please solve more questions related to that? And I will make sure you that probably we do have some kind of the specific sessions that will be just Q&A. I'm trying to design some kind of question, and then we are going to work on our calculation. Probably would be after one chapter or two chapters, because I would like to make sure that you guys completely understand it, everything related to series. Then we can move on to the parallel. And also we are going to have a lab. On that lab we are going to put all of these components side by side and make sure that we can measure the voltage, current, or even is that make any sense? For instance, when I do have a voltage of 2 volts in calculation, am I also going to have it in my circuit itself? So we are going to see that. It will be so much fun. And again, thank you guys for being here today with me. If you have any question, comment, put it in the comment down below. Don't forget to like and share and comment. That would be so helpful. Have yourself a great day, night, whatever. See you around.